After VFS, we started DFS, depth first search, which is that you keep moving to successive neighbors in the chain till you repeat somebody. And when you repeat somebody, you will backtrack. So backtracking will be to the nearest location, nearest vertex, where there is a new object, unvisited vertex. Pseudocode is simple enough, but it is very tricky to analyze what the pseudocode does, because there are tons of properties, some of which you will see today across the day. So that diagram shows you how it works. It basically, you start with vertex V, which is labeled 0. So 0 is the depth first numbering. So 0 to n minus 1 is the labels that you will give to these vertices, n vertices, and m edges. So 0 you go to 1, then 2, 3, and then there is a repetition, so you backtrack. So this backtracks to 2, from which you visit, you go to unvisited vertex, which is 4. It becomes 4, then 5, 6, then again backtracking, so you go to, you try 5, you fail, then you go to 4, you fail, then you go to 2, you fail, at 1 you fail, then at 0 you succeed and you discover 7. Okay, 8 and then you stop. So this is the recursive pseudocode. So all your DFS based solutions that you will give in the assignment or in the exam or in the quiz, it has to basically follow this DFS travels and DFS subroutines, and you will make changes here. Okay, you make small changes here and then you can solve big problems. So one big problem we'll solve today in that side. Yeah, we have shown that DFS overall takes just linear time, n plus m, and we want to study DFS tree. So the red edges give you the DFS tree. Okay, this was not implemented in the pseudocode. The tree part is not implemented yet, but I gave another. But there is an implicit tree in the execution anyways. So what is this tree property? So first is that it is not unique, because you are making these arbitrary choices. Right? Which neighbor to pick first and explore. That choice is arbitrary. And that, as we have discussed, depends on how the input was given by the user. So for the same graph, different ordering gives you different DFS trees. But still there are some fundamental properties. So main one is that the non-tree edges, which I was labeling B for back edge in the diagram, they are never like this. Okay, so XY is a back edge, non-tree edge. So this non-tree edge can never be like this, that you have orange thing. So okay, change the color maybe. That there is a DFS tree structure with left subtree, right subtree, and then within the subtrees there is an interconnection. That cannot happen. Okay, so in other words, the statement is that every back edge x to y, one of these is an ancestor of the other. Either x is an ancestor of y or y is an ancestor, which means that the y cannot be a cross edge to subtrees. There has to be an ancestral relationship. Is the statement clear? So what is being ruled out should be clear from this diagram. So how do you show this? So for this you use the numbering, the DFN array that DFS produced. So suppose that the DFN that X came before Y in the DFS execution. So what this means is that in the execution X was seen first, right? And we are assuming that the graph is connected. Okay, it is a connected graph, so the DFS tree covers all the vertices. There is only one tree. There is only one connected component. So when X was visited first, so DFS X started and Y is still unvisited, right? Remember that in the code there is a visit array also which is maintained. So DFN and visit both are arrays. Initially everything is unvisited. So Y is unvisited when X was visited, and then DFS X starts and then it proceeds, and at some point it will reach Y, right? At which point you will get the DFNY number. So DFS X would visit Y, and when it visits Y, it means that it becomes a descendant in the tree. So just because of this, what you learn is then Y is a descendant. Of X in the tree T. Okay, so this is the root. After a while it reaches V, and then something else will happen below Y, and from the root it had come to X. Okay, so in this tree which is red edges, Y has to be then a descendant. We are using that G is a connected graph. Is this clear? So that is one case, and this is all the cases actually, because the only other case left is that the number of X is bigger than the number of. What happens then? Yeah, this is a symmetric case. First case was that the number of X is less. Second case is number of X is large, but if number of X is large, then Y was seen first. Then Y will be an ancestor. So that finishes both the cases. So either Y is a descendant or Y is an ancestor. Okay, so, well, it seems that we did not even talk about the back edge, but we are talking about that because we wanted to make a statement about this edge. So I should correct this. So this is the back. Okay, so there is an edge connecting x to y, but what happened was somehow DFS of x bypassed that edge. It took some other route. So in the tree, this y to x or symmetrically x to y is a back edge. Okay, and you can see that in this case x is an ancestor. Or if the numbers are opposite, then also same thing. So one of these x or y is an ancestor of the other. Is this clear? So when there is a back edge, clearly there are two ways to reach. Okay, and DFS has used only one way. It has used exactly one way. So other becomes other way is edge, and that is called the back edge. Okay, so that finishes the structure of the edges. So there are two kinds of edges. Either x to y is a red edge, which is the tree edge, or it's a back edge. In which case it is always this picture, second picture, where you have this ancestor-descendant relationship. Any questions? What does that mean? So suppose you want to connect towers, cell phone towers, uh, in a way that if one of the cell phone tower breaks down, still the connectivity is not lost. Okay, so this is what is meant by robustness. So which means that even if so as long as only one tower breaks down, the connectivity is there. But if two of them break down, maybe then it becomes disconnected. Okay, so we call such graphs bi-connected. So graph G is called bi-connected. If for all the vertices in the graph, vertex that is degree, graph minus this vertex is connected. And I should say that we are looking at a connected graph. Well, connected and undirected also. Okay, so G is a connected undirected graph, and we call it bi-connected if for every vertex, when you remove the vertex, the graph is still connected. Is this clear? So, if somebody designs a network, which it's a graph, vertices are towers, edges are connections, either by air or by land. So your job is to check whether this is a robust network or not. How do you do this? This means that G is immune to single node failure. Okay, so single nodes can fail, it will not matter. The rest of the vertices will still be connected. Here I'm abusing the notation of set. So I'm saying G minus V. G is a pair, right? So by this I mean that remove the vertex from big V and also remove all the edges in which V is involved from E. Okay, so both V and E will change. That is what is meant by this notation. So let's see some examples if you have not understood. So is G1 bi-connected or not? It is, right? This one? This is also bi-connected. It looks like bi-connected. Any vertex you remove, you kind of are left with a line, not an isolated vertex. But if you have something like this happening, then what? Yeah, so then this vertex with degree 4, right, that is a bottleneck. So if that fails, then the network fails. So this is a one node failure, single node failure. So G1 is bi-connected. But G2 is not. Is this clear? Okay, so what is the first idea for this algorithm? Checking bi-connectedness. So first idea is just by the definition. You go over all the vertices and remove them one by one, right? So you go for all V in V, do one of the traversals, so BFS or DFS on G minus V to check connectedness. So the time for this is, so it becomes quadratic because you are doing n times O of n plus n. Right? So this is, first was linear, now you are making it quadratic. So this is order mn actually. Because m has to be at least n. Why is that? It's a connected graph, right? In particular, there is a tree sitting inside. A tree which connects all the vertices. So number of edges cannot be less than by n minus 1. So this expression is order m times n. M can be much bigger than n. Right? So this is quadratic, but in n it can even be cubic. M can be n squared, so this can be n cubed. Right? So this is not a good algorithm at all, especially for like social media kind of network. You simply cannot afford n squared or m times n, because you have then again the problem of 7 million square. So what you want is you just want to do one DFS and solve the problem. So is this feasible? So solve it in one DFS. Okay, so we just want to use the DFS tree and we want to check this property that there is no weak node, which if you remove, then the graph becomes disconnected. So for this, we have to do some graph theory. Okay, this is not just simple DFS analysis, but you have to be conversant with a property graph theory, which is obviously related to that weak point. So that point is called an articulation point. Okay, and what we want to do is that in a single DFS or constantly many DFS, we want to find all the articulation points. Okay, not just one, but all possible articulation points will be found. So let us work with that. Let us study properties of that. So vertex V in G is called an articulation point. If G minus V is disconnected. Okay, so these weak vertices, give them a name, which is articulation point. And we want to enumerate all of them in a given graph, given undirected connected graph. So for that, we cannot do this in one step. We have to do this after studying a lot of properties of articulation point. So the first property comes from almost from the definition, which is, let's draw that maybe first. So if X is an articulation point, so from general vertices U and V, there will be these paths. I mean, U or V, there may be a path without using X, or there may be a path using X. And what you are given is that when you delete X, then the graph gets disconnected. Right? So then the graph gets divided into two parts when you delete X. Which suggests that there has to be two vertices U and V such that, correct, so this is such that to reach from U to V or V to U, you have to go through X. So every path involves X. Okay, so there are such special U and V. This is not true for every UV, but there exists such UV. And X then becomes an articulation point. So let us record that. So vertex X is an articulation point if there exists U and V distinct vertices in V minus X, such that this picture, right? So which is saying that every path U to V passes through X. fact, this I want as a property. So let me just say this, if and only if. Okay, so vertex X is an articulation point, then there are these magical vertices UV, such that in any way if you want to reach U to V, you have to pass X. And if there are these vertices U and V, then it means that X is an articulation point, right? Because if you delete X, then U and V get disconnected. So clearly the graph is disconnected. So proof of this is easy. So if X is an articulation point, then G minus X, let's call this graph G prime, this is disconnected. Which means that there will be vertices in G prime. Such that there doesn't exist a path. Okay, so G prime is a new graph where we have removed the vertex X and also the edges incident on it. But by articulation point the definition, it's a disconnected graph, which means that there has to be minimum two vertices which are unreachable from each other. Let's call them U and V. But you know that U and V were connected before in G. So since they were connected before and now they are disconnected, so the only change that has happened is X is absent, right? So this means that every path must be passing. Passes through X. Okay, so that is the forward direction proof. The converse is clear. Similarly. Is this clear? So that is the first property of an articulation point X in the connected undated graph G. And so you immediately learn that G has no articulation point. Then it means what? No articulation point means that the graph is robust, right? So G is biconnected. In other words, if G is not biconnected, then there is an articulation point, at least one. So our now goal is to find all of them. We want to enumerate all the articulation points. And we want to do this by one DFS. How do you do this? So the idea is that you think of articulation point see the definition of articulation point or biconnectedness did not use DFS. That's a purely graph theory property, right? But since now you have been taught DFS, so you should first do DFS and then think about where can you see articulation point in the DFS tree. So think of articulation point X after drawing the tree. DFS tree T. G is a connected graph, so it will just be one connected tree, one tree, not a forest. And so what are the possibilities in that tree of an articulation point? So there is a root, and let's say X is an articulation point. So where can U and V be? The U and V which make X an articulation point, where can they be? So can it happen that they are of this type? I mean, first of all, how many possibilities are there for X, U, V to be arranged in the tree? That itself is a bit complicated. Right? There are many boundary cases, so it can happen that U comes first, then X, then V. Or it may happen that both U and V come after X, and in that also U may be a descendant of V. Or the third case is that UV look like this. So instead of going over all the cases, we don't have so much time to draw everything. Let us just fixate on this case and think about what does it mean that X is an articulation point with respect to this pair UV. So if you delete X, then there should be no path from U to V. You already know that these triangles don't have a path, right? These are different parts of the tree, so there is no edge here. So, but there may still be edges of this type. So it is still possible that when you delete X, the subtrees have paths going above X, which means to an ancestor of X. Right? So when that happens, then from a descendant of you can go to ancestor of X. And then from there, you can take a cheating path to a descendant of V, and then go to V. Right? So it will not matter if you delete it. So these kind of things are then absent. If X is articulation point with respect to UV pair, then this is not, one of these has to be missing. Okay, so let us say the subtree of U has no way to go from a descendant to an ancestor of X. Right? If both U and V have this property, have a way to go from descendant to ancestor of X, then clearly X is not articulation point with respect to this pair. And if one of them, let's say descendant of subtree of U, there is no such path, then it's fine. Then X is an articulation point with respect to this pair. Is this clear? That is how DFS tree is being used. Well, that is the plan, but it's, implementing this is still a bit complicated. So what have you observed? So let me introduce introduce the child Y, where this going up is forbidden. Okay, Y is child of X. So Y has in this picture two children. Other one I am not naming, the first one Y is what I make a statement. There exists a child Y of X, in the DFS tree that has no vertex in the subtree of Y with a back edge. Okay, so let's read this. So this is the first, this is the hypothesis that this picture depicts, that there is a child X has many children in the DFS tree, and there is a child Y, we call it Y, that has no vertex in its subtree with a back edge to any of the ancestors of X. If this doesn't exist, so when this happens, then I want to claim that X is not an articulation point. Is this clear? Any confusion or misunderstanding in the statement? If there is no back edge, yeah, maybe I'm making a mistake. X is an articulation. Yeah, so why is that? I think logically some of you have seen how it should be. So the reason is this: in this picture, there is no way once you go down Y from X in the DFS tree, there is no way to go to bypass X, to go above X. So which means that, in other words, when you delete X, there will be some vertex U in the subtree of Y, from which some vertex V in the other child of X, subtree of that, will be impossible to reach, irrespective of what happens in that part. So maybe I need to name that also. Irrespective of what happens on the Y prime side. So because of the hypothesis on Y, irrespective of what happens on Y prime, there may be a back edge, there may not be, that goes above X, doesn't matter. Because even if you take that new path going above X, you cannot actually come down to Y, subtree of Y. Okay? So that is the idea here. And this is if and only if. So yeah, maybe I should add a hypothesis here that X is neither a root nor a leaf. So we are actually talking about an X here, where X is an internal node in the tree. So when it's an internal node, then you can talk about, then you know that it has children. It has one child. Okay, so this statement is not vacuous. So X has a child Y, and X has a parent, or because its ancestor is root. Okay, so both the part above and the part below is non-vacuous. So using this, you can actually give a proof. So no bracket from subtree of Y to ancestors of X. Okay, this means that when you delete X, disconnects this part. So just complete this based on this hint, complete it as an exercise. The main idea is basically this picture. So when X is an articulation point, there has to be this special child Y. At least in the non-root, non-leaf, it's internal loop. So the, sorry? Yeah, so root and leaf we'll discuss now separately. So that is what remains. So those are the boundary cases, but they will be quite easy. So let's look at a leaf. X is a leaf. So I claim that, well, so in this case, can it be an articulation point? Yeah, so it's not an articulation point. Because X is just, if it is just a leaf, then it just sits here alone in the tree. If you delete it, you delete this edge, nothing changes in the rest of the graph. It remains, the tree remains connected. So deleting this doesn't change anything. Okay, so that is pretty easy. Last case is X is the root. What can you say in this case? So again, the previous diagram can give you an idea. X itself is the root in that diagram. So there is no ancestor to go to. Sorry? Exactly. So you have to look at how many children does it have. So if there are two children, Y and Y prime, then obviously they will get disconnected. Right? Because everything else that I have drawn in the diagram is hypothetical. So you can come from Y to its subtree, but then you cannot go back to an ancestor of X because there is no ancestor. So when you delete X, these two are Y and Y prime are disconnected. And if there is no Y prime, if there is only one child Y, then what? Then doesn't matter, right? Then the same thing as the leaf case. You can delete X all you want, but it doesn't change the connectedness of the tree. So X root meaning means that it's an articulation point if and only if X has greater than or equal to 2 children. So these are the cases. So this finishes all the cases. Internal node, leaf and root.
So but if X has greater than equal to 2, it need not be an articulation.
No. So look at the picture. x is the root and you have y and y prime here and subtrees and maybe more here. But what happens when you delete x?
No, but are you assured that y and y prime are then not connected?
How will they be connected? This is the DFS tree. Where is the back edge? That is what you need in the proof. So maybe this needs a proof. So when you delete x, y to y prime, there cannot be a path. Because the DFS tree is in front of your eyes, all that is missing is a back edge. But then where will you draw the back edge? Because back edge cannot go from across the two subtrees. It can only go above. Can be connected only by a back edge. But this non-3H property forbids it. Okay, so we had a non-3H property beginning of the class. So this non-3H property says that back edge, then endpoints have to be ancestor descendant. But unfortunately, when you delete x, y and phi prime are ancestor free. Right? So it's not clear where will you draw the back edge. It doesn't exist. You have to draw a back edge, multiple back edges, so that from y you can go to y prime, but that's not possible because you are looking at subtrees. So you can work out the proofs. Leaf is pretty clear. Other internal node and root, you can think about this. Finish the proof. If these are the main properties. We may not have time for the pseudocode. Okay, so based on this, we want to define now something on which the pseudocode will build. Okay, so that we need to define a new array. So that array has to do with the information about where this back path is going. What is the ancestor of x? Okay, so we want to store, let's say at y, the value of the earliest ancestor of x, which is reachable from any of the descendants of y. Okay, so we need that information now based on these motivated by these properties. So we'll call it a high point. So for v in the vertex set of the graph, define high point to be the DFN of that highest ancestor. So let me complete this in the class at 250. We complete this definition and then we build this array in a full pseudocode that we can implement.